All right, question number 4. The reaction between hypochlorous acid water is shown above. So this is a weak acid that is dissociating. Part of the reason we know that is because we know it's not one of our 7 strong acids, and we also see that equilibrium sign. Identify part A, one of the conjugate acid-base pairs in the reaction. Obviously there are 2 of them. You could say HClO and ClO minus. That's one of the, this would be the acid, this would be the conjugate base. It doesn't say to identify them, I'm just clarifying that. And then the other acid base pair, you could have said H2O and H3O plus. Again, that would be the base, that would be the conjugate acid again. So either this answer or this answer, but you can't say HClO and H2O. That's not an acid-base pair. It has to be the acid and its conjugate base, or a base and its conjugate acid. That is just a 1-point response. Okay, part B basically says, all right, if you change that HClO for HClO4, you go, oh, wait, first of all, that's a strong acid. And so one of the things I did is I thought, well, if that's a strong acid, then it's HClO4 completely breaking apart into H plus and ClO4 minus. So whatever the concentration of this is, that's the hydrogen ion concentration as well. So the hydrogen ion concentration is 0.200 molar. So to get the pH is equal to the negative log. So I took the negative log of, the negative log of 0.200, and I got the initial pH of the HClO4 is 0.74. And the reason that I did that is because now if I'm going to draw the graph, where does the pH start? It starts down here on the graph. It comes over. The equivalence point happens at the same point. So it happened at 25 before. It's going to happen at 25 again. So I'm going to come across. I'm going to come up really quick. Make sure that equivalence point happens. Again, we want that pH at the equivalence point to be right at 7, which it is. I probably could have made that line coming up a little bit more than I did, instead of saying completely flat or even kind of down, maybe kind of like this, and then whoop, and straight up, and then over, just like the other one. Okay, now that was actually a 2-point response, 1 point for the general shape, so 1 point for does it look like a titration curve, does it stay mostly flat, and then does it get really, really steep. So that was worth 1 point, and then the other point was having the pH at the equivalence point be right at 25 milliliters. So that's 1 point for the shape, and then 1 point for having the equivalence point at the right point. Okay, and then part C says a student proposes creating a buffer solution by dissolving some NaClO4, which is Na plus and ClO4 minus, in 100 milliliters of HClO4. Explain why that would not be a buffer solution, simply because HClO4 is a strong acid, not a weak acid, and would therefore not form a buffer solution. Okay, and that's really all you'd have to say on that. Part C was worth 1 point, and so there's your 4 points for question number 4. Question number 5. We've got some NADH. And let's see, so in part A, you've got the chemical reaction there, you've got the cell potential. It says how many moles of electrons are transferred for each mole of O2 that reacts? Justify your answer in terms of the balanced equation and the change in oxidation number of oxygen. So here the oxidation number of, here it is 0, here it is -2. Okay, and there are 2 oxygen atoms that do that. Okay, and so we can see overall, if each oxygen goes from a 0 to a -2, and it happens twice, that's 4 electrons that are transferred. Okay, you can also look at it as, take this second equation, and we're going to have to flip it to make the overall equation, and once we flip it, we are going to have to double it. So that's going to become a 2, that's going to become a 2, that's going to become a 4. So we can see in both cases that 4 electrons are being gained, 4 electrons are being lost. So for part A, you're going to say 4, and you're going to say because 2 oxygen atoms, because again, they're talking about the balanced equations. So there I am talking about the balanced equations. Go from a 0 to a -2 oxidation number. Okay, and that since A, B, C, D, obviously 1, 2, 3, 4. Each of these answers are worth 1 point each. Okay, part B, calculate the cell potential of the overall reaction. So we know that it does generate an electrical potential, and it doesn't involve in adding any electricity to it. So we know that that has to be a voltaic or galvanic cell. So the cell potential has to be positive. So it's going to be 0.815 minus a negative 0.320. Please don't mess up those double negatives there. And you get an answer of 1.135 volts. Obviously a 1 point response for having the correct answer. Make sure you absolutely show your work. Part C, now calculate the value of delta G. Delta G equals negative NFE. So we've got negative, and then our number of electrons that are transferred is the N value, that's 4. Faraday's constant, 96,485 joules, or 96.485 kilojoules per volts mole. And then our cell potential is the 1.135 volts. Put that into your calculator. Delta G equals negative 438 kilojoules per mole. Okay, and obviously just a 1 point response there as well for the correct response there. Part D, when the concentration increases while the concentration of NAD plus decreases, will the cell potential increase, decrease, or remain the same? So looking at, and even though here's our overall equation. So while the concentration of NADH increases, so while this goes up and this goes down, so clearly the reaction is proceeding that way in this case, will the potential increase, decrease, or remain the same? Well, the Q value, if you think about Q, remember we're comparing Q versus 1 here, not Q versus the equilibrium constant, Q versus 1. So Q would equal the concentration of NAD plus, and then the NADH plus the other reactants would also be on the bottom. But these are the two that we care about. And we said that NAD plus, that is going to decrease. So that decreases, and NADH is increasing. When that happens, that makes the value of Q decrease, and that's going to make Q less than 1. And when Q is less than 1, that increases the driving force. So will the cell potential increase, decrease, or remain the same? It will increase. And you'll just say when Q is less than 1, the driving force increases. Okay, just a 1 point response there as well. So that is out of 4. Okay, question number 6. So this is about some wax, some paraffin wax that's melting and freezing. It begins to melt at 37 degrees Celsius. So it has a melting point of 37 degrees Celsius. And it says, while the wax is melting, is the net flow of thermal energy from the wax to the surroundings, so that it represents an exothermic process, or from the surroundings to the wax, that is an endothermic process? Well, just ask yourself, when something melts, does it give off heat, an exothermic process, or does it require heat? Well, you're weakening those intermolecular forces, and so in order to do that, you absolutely need some heat. It requires some heat. Okay, so part A is you're going to say from the surroundings to the wax. Okay, and this is just a 1 point response, and I would just say something to the, because you have to justify it. Melting is an endothermic process. Something along those lines would be great. Okay, and that's a 1 point response. Okay, part B. Also a 1-point response. Calculate the amount of thermal energy in kilojoules that's required to melt 15 grams of the paraffin when the temperature is above the melting point. They give you the molar mass, and then they give you the enthalpy or the molar heat of fusion. So I've got 15.2 grams. Well, what's the only thing I can do with grams? Convert to mole, 282.62 grams per mole. Okay, and then we can say we've got moles on the top, so we're going to put 1 mole on the bottom, and we're going to put the 48.78 kilojoules on the top. There is no reaction here. Notice they don't say kilojoules per mole of reaction at this point right here. And so that's not something that we need to concern ourselves with. If we did, between here and here, we would switch from moles of paraffin to moles of reaction, but there is no overall reaction. It's just something that's melting. Okay, so we divide, multiply, we get 2.62 kilojoules as the final answer there. Okay, and again, they're talking about the amount of thermal energy that is required, so they're not talking about a positive or a negative number. They know the heat is required. Okay, part C is a 2-point response. When paraffin wax melts, its density decreases. Provide a particle level explanation of this observation. Okay, so first of all, I would say in a liquid, the distance between the molecules is greater. Okay, so that was 1 point. You had to say something about in a liquid, when it's solid, they're more compact, the molecules are closer together. In a liquid, in general, they are farther apart. Water is an exception to that. We know that ice floats because it's less dense because of the shape that water forms when it freezes. So 1 point for talking about how when something goes from a solid to a liquid, the molecules are farther apart from each other. Okay, and so the second point was talking about the greater the distance, the larger the volume required. And again, if you only talked about volume, how a liquid has a greater volume, then you can go ahead and give yourself 1 point for that. But that is a 2-point response. One for talking about why is the volume bigger? Well, because when the things are solid, they're closer together. And when they turn to a liquid, again, other than water, they're farther apart from each other. Those intermolecular forces aren't as strong, which again, the stronger they are, usually the closer they are together. Okay, so that is a 4-point response. And now we are on to our last question. Question number 7 says a student is given a solution of phenol red of unknown concentration. Solutions of phenol red are bright pink under basic conditions. So kind of like what we're used to with phenolphthalein, kind of that pink color. Phenolphthalein is clear when it's acidic, but it's bright pink or a purplish pink when it turns to a base. So A says the student uses a pH probe and determines that the pH of the solution is 11.2. Calculate the hydrogen ion concentration in the solution of phenol red. Okay, so if the pH is 11.2, we know that from pH you can take 10 to the negative pH, and that gives you the hydrogen ion concentration. So we just simply need to take 10 to the negative 11.20 and 10 to the negative 11.20. Remember, with pHs, only the last 2 digits count for significant figures. So technically our answer should only have 2 significant figures in it. So I got a hydrogen ion concentration equal to 6.3 times 10 to the minus, not second, to the minus 12th molar. Okay? And that was a 1-point response. Okay, that says the student analyzes a sample of the solution, uses a spectrophotometer, set at a wavelength of 559 nanometers. The wavelength is that's the maximum absorbance for phenol red, and then the measured absorbance at 559 is 0.35. Based on the calibration curve shown below, what is the concentration of the solution in micromoles per liter? What the heck is that? Who cares? There it is. Micromoles, which is micromolarity, is micromoles per liter, which is that, again, that micro M. Don't let that part confuse you. Okay, so all that we're going to do is we're going to go to 0.35. We're going to come over on our graph to the line. From the line, we are then going to come straight down, and we're going to have an answer kind of in the 5.2, 5.3. I will tell you they accepted any answer from 5.2 to 5.6. So if you got anything in there, you got the point for it. And that obviously a 1 point response, so that takes us up to 2 points. Okay, part C says, if the student mixed 10 milliliters of distilled water with 10 milliliters of the sample, would this diluted solution have an absorbance greater than, less than, or equal to the absorbance of the original solution? Well, when you add water to a solution that's colored, of course the amount of color is going to go down because you've diluted the solution. And when you dilute the solution, again, they're talking about absorbance. Is more of that light going to be able to pass through? Is less light going to be able to pass through, or the same amount of light? Okay, certainly more light is going to be able to pass through there, which means the absorbance is going to decrease. Okay, so for part C, you're going to say less than. Okay, and then to justify your answer, I said the lower concentration results in less light being absorbed, okay? And that's all you'd have to say there. Okay, 1 point response there. And then part D, if the student measured the absorbance of the solution at a wavelength of 650, would the absorbance be greater than, less than, or equal to? Well, they already set up above that the maximum absorbance occurs at 559. So any wavelength other than 559, you are not going to get the maximum amount of absorbance. Okay, so on part D, there's no choice other than less than. Okay, and you would simply have to justify that by saying 559 nanometers is the maximum absorbance. So, and then like I said, any wavelength other than 559 is going to result in less of that light being absorbed. Okay, and that is a 4 point response. Get your score out of 4. So again, overall, multiple choice, you've got a score out of 50. Put your number in there. Free response. Take your score out of 46, times it by 1.0869, and get a new score out of 50. Add that number and that number together to get your score out of 100. Okay, and your score, this one, if you remember those first 25 multiple choice, they were fairly easy. And so the scoring's a little bit higher on this. To get a 5 on this, you had to get anywhere from 82 to 100 was a 5. Okay, the 4 stopped at 70. So 70 to 81 is a 4. 52 to 69 was a 3. So almost down to 50 there. The 2 did go all the way down to 37. To 51 is a 2, and then obviously 36 and below is a 1. Okay, and that is the 2019 practice test. Peace. I'm out.